accumulate our records. So you need a place to put them that's organized in a way so you can find information easily. Something like this. For hundreds of years, no matter what you were selling, the process of doing business came down to these basic steps: recording, managing, and organizing certain key pieces of information. And for most of that time, it was all done with this or these and lots of paper. All along, there was a simple process driving the evolution of the business office. The faster you could write things down, the more organized your records were. The more efficiently you could send out bills, the more money you could make. A more efficient office was a more profitable office. And people realized this early on, and they came up with all sorts of simple innovations in the business environment. Things as simple as this letterbox, for example. It's a temporary storage space defining work coming into and going out of your particular area of responsibility. It really helped improve efficiency. We still use them. Small improvements like this came along rapidly all through the 19th century. But when electricity came into the picture, the business office was transformed. With the telephone and the teletype, you could take orders, promote products, and send bills out to customers thousands of miles away in a fraction of the time it would take to do it by mail. Early dictating machines enabled a person to prepare correspondence and instructions to be acted on later, giving people a more effective way to manage time. And calculating machines freed business accountants from the centuries-old limitations of pencil and paper. All these developments helped increase the pace of business in the early 20th century to a level never before possible. By the 1950s, a technology boom was pushing things even faster, bringing time and labor-saving innovations to the business environment almost daily. And then in the 1970s, business equipment manufacturers got hold of this, the integrated circuit. And things would never be the same.
With the introduction of large-scale integrated circuits and the new products they made possible, the business environment was no longer simply mechanized. It had become automated. Office automation has revolutionized the way we do business. It's given us voice communication systems that are more efficient and more flexible. It enables us to exchange visual or electronic information between customers and suppliers any place on Earth in a matter of seconds. And for record management, it can put the power of electronic data processing on a single desktop, all at a cost easily tailored for even the smallest company. When we need the convenience and portability of paper, office automation technology provides a full range of options. Our business information can be printed, reproduced, or destroyed.
You're watching the first in a series of programs devoted to office automation basics, the fundamental processes that make some of this technology possible. In this program, we're going to look at copiers. But before you learn how copier technology works, it helps to understand its history. And before you focus on that, make sure you make the distinction between copying and printing.
Copying is an office concern, making small quantities of just a few pages or even a single page. Printing is an industry by itself, devoted to producing very large numbers of one page, often for the purpose of making a book, magazine, or newspaper. Printing technology experienced innovations and increased efficiency long before any such advancements came to the world of copying. Offset printing and mimeograph equipment produced hundreds of copies a minute for little more than the cost of the paper, but they were only practical if you wanted to make hundreds of copies.
What business offices needed was a way to make single copies that was inexpensive, very fast, and used hardware that was easy to operate. And until the 1960s, most offices relied on this, carbon paper. Well, you talk about business traditions. Carbon paper had been around since about 1900. It was certainly cheap, and if you used a few sheets and you pressed hard enough, you could get 3 or 4 copies in one shot. Of course, you had to know you wanted those copies while you were creating the original. And if you wanted to copy a letter from someone else,
Carbon paper couldn't help you at all. For that, you had to rely on conventional photographic methods involving a camera, wet chemicals, washing and drying time. Not the kind of system you need to get a quick report out the door.
The first important advancement came in 1953 from the German photographic giant Agfa Gewehrt. They introduced the diffusion transfer process, shown here with modern equipment. The process still used a camera, but no negative. Instead, the image was exposed directly onto a special light-sensitive sheet called a master. After exposure, it was run through one chemical bath and squeezed against a transfer sheet with a pair of rollers. You waited a minute, peeled them apart, and you had a high-quality copy of anything. A big improvement, but you still got only one copy from each master. Not to be outdone, in 1954, Eastman Kodak introduced Verifax. This process photographed an original with a master which, instead of developing into light and dark areas, produced hard and sticky areas. The developed sheet was squeezed against special copy paper with a set of rollers, and the sticky image areas on the master adhered to the paper. The big improvement here was that you got about 10 copies from every master. Multiple reproduction was getting easier. In 1956, 3M Corporation introduced Thermofax, a thermal transfer process. Here's how it worked.
To start with, an original had to be created with some kind of heat-absorbing ink. Inside the machine, the original was heated very rapidly and then pressed against a special copy paper. Image areas on the original became hot enough to burn a copy into the surface of the heat-sensitive paper, like this. Thermofax had its drawbacks. You couldn't copy anything that didn't absorb heat inside the machine, particularly pencil. And the copies tended to fade. But it was better than anything else. Making a copy was fast, just a few seconds, and inexpensive.
In the meantime, other people were working in different areas, moving away from the established technology. In 1955, the E-stat process appeared. E-stat was a different approach to copying, very high-tech for its time. It used a direct electrostatic system, which exposed and developed an image directly on special copy paper treated with zinc oxide.
The paper was gray and difficult to write on, but the machine and the copies it produced were cheap enough to be within the budget of even the smallest company. Things were looking up.
Then, in 1959, the Haloid Corporation in Rochester, New York, introduced a machine that would change the way businesses create and distribute information. The machine used an indirect electrostatic process patented in 1939 by Chester Carlson, who named his invention after the Greek words for dry writing. It took him 11 years to develop the process and find the interested backers at Haloid, and then took them 9 years to perfect the design. But it worked.
They created the first plain paper copier. It could reproduce an original on virtually any paper in your office. Letterhead, graph paper, even on different sizes. The machine was fast, automatic, priced low enough to attract a wide range of customers, and the cost per copy was only a few pennies.
It became the biggest success in business equipment since the electric typewriter. And in 1961, Haloid Corporation changed its name to signify the process that had brought it so much fortune. In today's offices, copiers are as commonplace as fluorescent lighting. Speeds range from less than 10 copies a minute for a small desktop model to over 150 copies a minute for a large industrial duplicator. Capabilities can be tailored to a user's need and budget. A typical modern copier can make the image darker or lighter, bigger or smaller, feed documents automatically, and sort the copies into complete stapled sets. Sophisticated microprocessors give some machines features like page memory, automatic book copying, even editing. Copiers have redefined the way we do business, and helped set a direction for the development of office automation. We are now as dependent on them as we are on the telephone.
I'll send you a copy. Bye. You're welcome.
The machines being manufactured today use the same indirect electrostatic process as the original haloid design. It can be broken down into roughly 7 steps. In the following sections of this program, we'll take a closer look at each one. To the person using the machine, making a copy is a fairly simple process. Place the original, set a quantity and maybe a few parameters, and press the print button. But inside the machine are other processes responsible for producing those copies.
Before you can study these processes, you need to become familiar with the special material that's the foundation of electrostatic copying. It's called the photoconductor. There are several different types of photoconductors used in copiers today, but no matter what type is involved, the basic principles are the same. To get a good look at the photoconductor, you have to see inside the copier. We can't do that very well here, but we can over here. This is the same machine reduced to the most basic elements of copier technology. This round unit in the center is one of the most popular photoconductor designs, a selenium drum. This shape allows the surface to interact with other systems inside the copier simply by rotating on a central axis. Now, what's so special about it? You've seen this stuff before. You use it in a camera. Well, a photoconductor is to a copier what film is to a camera. It captures an image and changes it into another form. But there's a key difference between film and a copier's photoconductor. Film creates an image through a chemical process. A photoconductor does the job by setting up a relationship between light and an electrical charge. We see a similar kind of relationship in photovoltaic cells, what we often call solar cells. You've probably seen these before on watches or calculators. The cells in this solar-powered calculator are made from thin layers of light-sensitive material, a wafer of silicon with metallic coatings bonded to each side. When exposed to light, these cells produce electricity in direct proportion to the light shining on them. The brighter the light, the greater the voltage. A photoconductor is also made from layers of different materials, but it's not designed to produce electricity. Instead, a photoconductor stores electricity on its surface in an inverse proportion to the light shining on it. That means the brighter the light, the less electricity it can hold. Don't think of it as a single battery storing a single charge. A photoconductor is more like a surface made from millions of microscopic batteries, each one able to store and discharge electricity independently.
The photoconductor doesn't produce this electricity itself. Every copier has a charge system that gives the photoconductor an electrical charge right at the start of a copy cycle. Remember the meaning of xerography, dry writing? Well, this charge is what something being copied is actually written on. The photoconductor can't capture an image without it.
We'll concentrate on this system in the next section of this program. But for just now, just assume that the photoconductor has a uniform electrical charge over its entire surface. Let's look a little deeper into that surface. If you take a slice through here and magnify the cross-section, the individual layers look like this. On the bottom is a layer of aluminum to give structural support. The aluminum is oxidized slightly, so it has a better grip on the next layer, a thin coating of selenium. Finally, a layer of selenium oxide is formed on top, creating what's called the trapping layer. It's the special electrical properties of selenium that make this combination effective. Selenium's electrical resistance varies with its exposure to light. In the dark, selenium is an insulator, and it won't pass electricity. But you shine some light on it, and it becomes more conductive. With enough light,
There's virtually a direct connection through the selenium between the trapping layer and the aluminum base, a connection that doesn't exist in the dark. Here's what that means in Copier terms. By exposing a photoconductor to a pattern of light that matches an original image, you can use it to make an electrical copy of whatever appears on that original. We've spent all this time talking about the photoconductor because it has such a central role in the copy process. Once you understand it, you can examine the major steps in the process and learn how the different groups of components interact. Each of those steps will be covered in a separate section of this program, but to give an idea of the type of systems involved, I'll take you through a quick overview of the whole copy process, start to finish. In a copier this size, the whole process takes about 6 seconds, from pushing the print button to walking away with your copy. Here's where we start. We already mentioned that the photoconductor needs an electrical charge before it can capture an image. This charge process is the first step, and it happens just after the drum starts turning. This component here, the charge corona unit, applies a charge to the photoconductor surface. After being charged, the drum rotates down to here, where an original image reaches the surface. This is the exposure process. The image is reflected from an original by several mirrors focused through a lens, and finally directed onto the photoconductor. Remember, all this happens while the drum is turning and with no other light present except what the copier is providing. After exposure, the image is electrically stored on the drum surface, but you can't see it yet. It's still only a pattern of electrical charge. At this point, we're about 2 seconds into the copy cycle. The next step is making that image visible, development. The drum's rotation brings the image area into contact with this item, the development unit. Using a combination of mechanical, electrical, and magnetic processes, this unit brushes a fine black powder over the photoconductor. The powder only sticks to the charged areas, so it creates a visible copy of the original on the drum. The next step is getting a sheet of paper into the copier, positioned so it can pick up the developed image. That's the process of paper feed. There's a paper supply over here. The copier's control system regulates feed rollers, which pull one sheet of paper from the supply and move it through the machine during each copy cycle. Okay, you've got a developed image and a sheet of paper. Now you have to bring them together. The transfer process takes place here, at about the 3-second mark. In the transfer process, an electrical field is produced by this unit, the transfer corona. The field pulls the coating of black powder away from the drum onto the sheet of paper. The distribution of this powder matches the original exactly, so the paper becomes a copy. Right after the transfer comes the separation process. The sheet of paper moves with the drum and passes over the separation corona. This unit produces another electrical field which frees the paper from the photoconductor. The sheet of paper now carries a visible image of the original. It moves away from the drum and passes between these two rollers. These are the fusing rollers, which apply heat and pressure to the copy, creating a permanent bond between image and paper. After the fusing process, the copy's finished. But the copy cycle has one more step to go, the cleaning process. It happens back on the drum. The drum's rotation brings the photoconductor surface in contact with the cleaning unit. The cleaning process prepares the photoconductor for the next copy. First, a mechanical system removes leftover powder from the drum surface, anything that didn't transfer from the developed image to the paper. Then, a special lamp shines light on the photoconductor to remove the pattern of electrical charge from whatever was just copied. The drum now has a clean and electrically neutral surface and is ready to repeat the entire chain of processes for another copy. As you can see from this quick tour, nearly every step in the copy process involves the photoconductor, so you'll be hearing it mentioned a lot in the sections that follow. The first of those sections takes us to the starting point in a copy cycle, where the photoconductor is prepared to receive an image, the charge process. In the last section of this program, we looked at the photoconductor, the material that quite literally lies at the center of the copy process. A photoconductor is made from a certain material that varies its electrical resistance in response to light. The more light, the less resistance. Because of this property and its particular layered construction, a photoconductor has the ability to store an electrical charge on its surface in proportion to how much light is hitting it. This enables it to make an electrical copy of an image. That charge isn't created by light or by the photoconductor itself. It's produced by a special group of components during the first step in a copy cycle, the charge process, and it takes place right here. This item is the charge corona unit. As the drum begins to rotate at the beginning of a copy cycle, the corona unit is energized and gives the photoconductor an even electrical charge. The charge applied by the corona is a little different from the electricity we normally use. AC and DC currents in our homes and appliances both flow from one place to another. But the corona unit creates a charge that stays in one place, a static charge. Static charges can develop when certain materials are rubbed together. And we notice the charge because the materials involved start to attract each other. You may have seen this happen when combing your hair. If the hair is very dry, it will be attracted to the comb. Many types of plastic tend to develop a static charge this way. It happens with glass, too, under the right circumstances, and also with some synthetic fabrics, like polyester or nylon. Here's a piece of clear acrylic. This stuff can build up a very strong charge if you rub it with the right material, like wool. The rubbing action causes the charge to build up as two opposite polarities, positive and negative, and opposite charges always attract each other. Because only one polarity of charge builds up on the acrylic, it will attract anything that's close to the opposite polarity, even things that are relatively neutral, like these bits of paper. Though fundamentally the same as the static charge on this acrylic, the charge process in a copier has one important difference. What you see here is the result of mechanical action between two materials. In a copier, the charge process creates an electrostatic charge applied by an electrical field. In terms of polarity, most copiers create a positive charge on the drum, though for some types of photoconductors, a negative charge is necessary. For our purposes, we'll assume the copier has the more popular selenium drum, which gets a positive charge. As mentioned earlier, that charge is delivered by a corona unit, like this one. It's mounted about like this, very close to the surface of the conductor. The corona unit consists of a metal housing with an electrical connection at one end. Tied to that connection on the inside is the charge corona wire. It's this wire that actually applies the charge through a carefully regulated series of events. Here's what happens to it when a copy cycle begins.
Almost immediately after a copier's print button is pressed, a positive DC potential, somewhere between 5 and 10,000 volts, is applied to the corona wire. The wire isn't grounded, so this voltage can't really flow anywhere. What it does instead is cause a positive electrical field to build up in the air surrounding the wire. This electrical field spreads out from the corona unit toward the photoconductor and applies an even positive charge to the photoconductor's surface. Since this happens in the dark, the photoconductor is in a non-conductive state, so instead of flowing to ground, the positive charge on its surface keeps building up and reaches close to 1,000 volts. The copy cycle continues and the drum turns. Fresh, neutral photoconductor moves past the corona, becomes charged, and then moves on, ready to receive an image. A byproduct of charge corona discharge is the generation of ozone inside the copier. Ozone can oxidize the photoconductor's surface, reducing its ability to respond to light. An exhaust blower helps avoid this problem. It pulls air through the inside of the copier to prevent the buildup of ozone over the drum. This ventilation also ensures an even distribution of ions during the charge process. The charge corona housing is usually perforated in some way to take advantage of the airflow. The DC voltage for the charge corona is sent through a high voltage cable from a power pack, a device incorporating a step-up transformer, rectifier, and some special control electronics. A typical charge circuit works like this. The power pack is supplied with a constant low voltage directly from the copier's power supply. At the beginning of a copy cycle, the main control board triggers the power pack, which steps up the low supply voltage to the level needed for charging. The resulting output is sent through the high voltage cable to the corona wire.
That's the charge process. It starts with the photoconductor, a material that's an electrical insulator in the dark, but a conductor when exposed to light. Inside the copier, shielded from the light, the photoconductor gets an even electrostatic charge from the charge corona unit. This charge prepares the photoconductor to receive an image. Getting that image onto the charged photoconductor is the next step in the copy cycle. We'll go through it in the next section of the program, the exposure system. People who work with cameras are very concerned with light, its brightness, color, and direction. They have to be. It's only by carefully controlling light that they get the desired image onto a piece of film in here. There's a similar situation inside a copier. In a sense, a copier takes a picture of something. It focuses an image onto a light-sensitive surface. In the last section, we saw how the charge process prepares the photoconductor for receiving the image of an original document. That's how a copy cycle starts. The drum's rotation has moved the charged surface over to here. This is where an image is recorded in the exposure process. When you study a copier's exposure system, the first thing to consider is the way an original document affects the light that shines on it. The lighter parts of an original, like the areas of blank paper, reflect a lot of light, while the darker parts, like the letters and lines, absorb most light. Reflection and absorption create a visible pattern anytime something is hit by light, and the pattern is an exact image of the original. To capture an image with this reflected pattern of light and dark, copiers use an exposure lamp. It shines light on the original and reflects the image inside the machine. The next step is focusing. Under most circumstances, reflected or transmitted light can't create an image simply by falling on another surface. You see, the light is there, but there's no picture. That's because the original image has to be reassembled and in a size that's suitable for the application: projector, camera, or copier. This is done by something that collects light from the original image, a lens. It directs the light onto a surface at some predetermined distance, in the same pattern in which it left the original. Lenses take advantage of another property of light, refraction. This is light's tendency to bend slightly when it passes from one material into another. In a lens, that means going from air into glass and then back into air. Just as reflection makes it possible to produce an image from something, refraction enables us to reassemble that image. You add a lens to the system, and you can focus. The image is reassembled, and in whatever size the situation demands. Okay, here's the process so far. Light shines onto an original. The original reflects the light, creating an image through a combination of reflection and absorption. And the lens focuses the image onto a new surface. This works fine as long as the image is being projected onto a flat surface. And in large, high-speed copiers, that's exactly what happens. Xenon flash lamps expose an entire page at once, and the image is focused onto a large, flat photoconductor belt. But in most copiers, a flat original is focused onto a curved photoconductor drum. The drum design has a lot of advantages and makes the machine quite compact, but it creates some challenges for the exposure system. The curve prevents the lens from keeping the image in focus over the entire drum surface. There's also the fact that most drums have a smaller circumference than a typical letter size original, one page actually wraps around more than once. Copiers get around this problem by scanning the original a little at a time while rotating the drum. In a scanning system, light is reflected from the original through a narrow slit. The original is moved across the slit at a constant speed while the drum turns at the same speed. In a few seconds, the entire image is wrapped around the drum in perfect focus. In a scanning operation, the machine avoids overlapping the image on the drum by removing the essential image details before the drum has rotated all the way around. More on that later.
There are two kinds of scanning. Some copiers actually do scan like our example by moving the original on an exposure surface called a platen across a fixed slit and exposure lamp. Others keep the platen fixed in place and use a moving scanner assembly with a slit and exposure lamp. Both systems work. The former design is suitable for relatively slow copiers, while the latter is used on medium to high-speed machines.
Here's the exposure process so far. An image is reflected from the original with an exposure lamp, scanned at the same speed as the drum's rotation, and then focused through a lens. But you may have noticed a problem. Using the appropriate lens for an average original, this light path has to be about 4 feet long. This would make even a simple copier about the size of the average desk. To get a big light path into a small box, you fold it, just like you would fold a letter to fit into an envelope. But to fold light, you use mirrors.
Here's a typical light path in a scanning desktop copier. There are 4 mirrors, 2 scanners, and 1 lens. The exposure lamp is mounted on the first scanner. It shines light onto the original, which reflects an image onto the first mirror. The light then folds left to 2 more mirrors on the second scanner, which fold the light down and to the right. The lens focuses and sizes the image, projecting it onto 1 more mirror, which folds it again. From here, the light is reflected down onto the photoconductor.
The mirrors used in copiers are called front surface mirrors and are coated with reflective material on the side facing the image. They're very susceptible to scratches. Typical household mirrors are coated on their rear surface, which makes them more durable but unsuitable for optical use. A rear surface mirror actually has 2 reflections, a strong one from the silver coating on the back and a faint one from the front surface of the glass. This second reflection goes unnoticed in most applications, but would produce a double image effect in a copier. Well, we've now reflected, scanned, and focused an image and folded the light path into a suitable size for a desktop copier. There's one more aspect of the optical system to consider: reproduction ratio. Most of the time you make a copy, it's the same size as the original. That's a 1-to-1 reproduction ratio. But sometimes enlargement or reduction is necessary for special applications. To do this, the copier has to change the reproduction ratio by moving some things around. It works like this. Here's an image, and here's an optical system. Now imagine that this wall is the photoconductor. So here's what we have. This projector can't produce a 1-to-1 ratio, but it doesn't matter for this example. I'll just measure the image on our photoconductor here. Okay, we have an image about 9 inches high. If you want to make the image smaller, what's the first thing you do? Well, generally, the farther you are from something, the smaller it looks. So to make the image on the photoconductor smaller, you have to move the lens farther away from the original. All right, the image is smaller, but now it's out of focus. To correct the focus, you decrease the distance between the lens and the photoconductor until the image becomes sharp again. To enlarge an image, you do the opposite. Decrease the distance between the lens and the original, and increase the distance between the lens and the photoconductor. Instead of moving the photoconductor drum, scanning copiers with a variable reproduction ratio keep the image in focus by moving extra mirrors in the light path. The mirrors move to make the distance from the lens to the photoconductor shorter for enlargements and longer for reductions. This system of changing the distance on each side of the lens is all you need for enlarging and reducing the image, if you're projecting the image onto a flat surface. This is the case in a high-speed copier with a flat photoconductor belt, as mentioned earlier. But the majority of copiers have a drum. Inside the machine, only the drum's horizontal dimension is parallel to the original. Its vertical dimension is a curve wrapped into a cylindrical shape. Because of the drum shape, moving the lens back and forth only affects the horizontal size of the image. Both of these examples show an image with constant vertical size, but a changed horizontal size. This one enlarged, this one reduced. A scanning copier adjusts the horizontal size by moving the lens, as you've just seen. But to adjust vertical size, it uses a completely different method.
Remember how scanning works? The scanner moves across the image at a speed matching the rotation of the drum. That's only for a 1-to-1 ratio. To change the vertical image size, you change the scanner speed. Here's a 1-to-1 ratio. Scanner and drum moving at the same speed. Now watch this. The drum speed is the same, but the scanner moves faster. See what happens? Since the scanner moves faster, but the drum turns at the same speed, the image covers less drum surface. It's reduced. Here's an enlargement. The scanner moves slower than normal, so the image is spread out over more drum surface. It's enlarged.
This is how scanning copiers handle reproduction ratio. Two systems: a moving lens and mirrors for changing horizontal magnifications, and variations in scanner speed for changing the vertical magnification. That's the optical system. The reflecting, scanning, focusing, and changing of size all have a common goal: bringing an image of the original to the photoconductor. When it gets there, it creates a sort of electrical copy. We refer to it by the same name photographers use to describe what's on a piece of film that's been exposed but not developed: a latent image.
As the process begins, light from an exposure lamp reflects the image into the optical system. The light is folded by mirrors while a lens brings the image into focus. After focusing, the light reaches one more mirror, which reflects the image onto the photoconductor. Since the image is a combination of lighter and darker areas, the intensity of the light carrying that image varies accordingly. The photoconductor is still non-conductive and carries a uniform electrical charge. When the image reaches the surface, it affects the photoconductor like this. Light from the dark image areas carries very little energy and has almost no effect on the portions of the photoconductor it reaches. Those portions remain in a non-conductive state and stay positively charged. But light from brighter image areas, like blank white paper, carries much more energy. When this light hits the photoconductor, it causes the surface to change to a conductive state. The charge on those areas flows to ground and dissipates almost completely. In this way, the light creates an invisible electrostatic copy of the original on the photoconductor, a latent image. It has a strong charge still present where the image is dark and almost no charge left where the image is light. Since the photoconductor is charged over its entire surface, the latent image always contains some detail that's not actually part of the information being copied. It's produced from dark areas beyond the borders of the original. This usually means marks on the document cover or the complete absence of reflection that results from making a copy with the cover open. Even the edge of the original document can produce a black line on the copy. Because these non-image areas still carry a charge, the copier will treat them as if they represent something dark on the original and make them visible just like the charged areas on the latent image. This is something to avoid. A copier makes the latent image visible by coating it with a dark powder or liquid. This material can accumulate inside the machine if too much drum surface is still charged after exposure, so most copiers use something to prevent it, an erase lamp. The erase lamp is a row of LEDs that runs across the drum just past the exposure area. Based on the reproduction ratio and the size of the paper being used, the control system switches on the LEDs in specific groups. Time to shine light on the drum surface at the leading edge of the latent image, on each side, and at the trailing edge. Just as in the exposure process, light from the erase lamp dissipates the charge on the photoconductor and changes the non-image areas back to a neutral, uncharged condition. Original documents vary quite a bit. Some are much more reflective than others, depending on the type of paper and the information contained. This could cause severe fluctuations in copy quality. To compensate for the variation in originals, copiers use some type of image density control, manual, automatic, or both, to adjust the brightness of the exposure lamp. Some automatic systems work like this. Before exposing the original, the copier performs a pre-scan check. In this operation, a fiber optic cable on the first scanner passes a reflected light reading from the original to a photosensor. Low reflectance from the original indicates a darker than normal surface. This usually means colored paper, which might cause a gray background on copies. To avoid this problem, the control system adjusts the exposure lamp voltage. When the sensor detects a dark original, lamp voltage is increased a certain amount to create a brighter reflection and a balanced latent image on the photoconductor. When the original is conventional white paper, no adjustment is needed. The normal lamp voltage allows the machine to produce a clean copy. The circuit for the exposure lamp usually involves a dedicated circuit board for high voltage control elements. To switch the lamp on, the main board triggers a regulator circuit on the high voltage board. Image density information, whether from an automatic sensor or manual control, is sent to the main board, which then passes a control signal to the regulator circuit. This circuit adjusts lamp voltage to the appropriate level, and a triac switches the voltage to the exposure lamp. Since a copier's lens and scanners move to do their jobs, the machine's control system has to know where they are before and during a copy cycle. One way to keep track of their locations is to designate a point in each component's range of travel as its home position, and then monitor that point with a sensor. Photo interrupters are often used for this. Small plastic blocks with a photocell on one side and an infrared LED on the other, separated by a narrow gap. Each moving component has an actuator that enters the gap, interrupting the light from the LED when the component is at its home position. This turns off the photocell and alerts the control system accordingly. With photo interrupters suitably positioned, the control system can tell when moving components are at or away from their home positions and determine if a new copy cycle can begin. For moving the lens, additional accuracy is needed, since only through careful repositioning can the copier produce consistent enlargement and reduction. This is done with a stepper motor, which can be controlled in precisely calibrated steps. Each step is a small fraction of one revolution and can be counted by the machine's control system. The home position for the lens is typically the position for a 1-to-1 reproduction ratio. When a different ratio is selected, the control system starts the motor and moves the lens the appropriate number of steps away from the home position. This produces a copy with the desired enlargement or reduction. To return to a 1-to-1 ratio, the lens is moved back to its home position.
That's the exposure process. During exposure, an image is created with reflected light, scanned with moving mirrors, and focused through a lens. The lens moves to make the image larger or smaller, while additional mirrors move to keep the image in focus. Finally, the image reaches the charged photoconductor. The light areas remove the charge from the surface, while the dark areas leave the charge alone. This creates an invisible electrical copy of the original on the photoconductor, a latent image. At this point, the machine has made an accurate copy of the original, but it's not in any usable form. Can't even see it yet. The next step in the copy process will make the image visible. Development. Here's an original, and here's a copy. We've been looking at the technology that gets us from here to here. Earlier in this program, we examined the photoconductor, the material that makes electrostatic copying possible, and we've seen how the charge and exposure processes create a latent image, an invisible counterpart to the original you're trying to copy. The key word here is invisible. Just like an exposed roll of film, the latent image on the photoconductor needs to be developed. In a copier, development relies on electrical attraction and magnetism. As the latent image moves away from the exposed area, for the first time in the copy cycle, the photoconductor comes into physical contact with another component, the development unit here. Now remember, the latent image is actually a pattern of electrical charge. That's what makes the development process possible. Inside the development unit, there's a supply of material, usually black, that's known simply as developer. Sometimes it's a liquid, sometimes a powder. We're going to look at the most popular system, which uses two different dry materials combined to make what's called a two-component developer. Here's one component called carrier. It has about the same texture as sand, but the individual particles are round, like little ball bearings. Carrier is made from an iron-based material, so the particles are attracted to a magnetic object. This quality is an important aspect of the system. Carrier is not used up during the copy process. It stays in the development unit and only has to be replaced when it wears out after many thousands of copies. The other component is toner, a much finer powder than carrier. It's made from resin combined with carbon or colored pigment. Toner isn't magnetic, but it will respond to an electrical field. Inside the development unit, toner and carrier are mixed together, and the toner gets an electrical charge that's opposite the charge of the latent image. Then a special roller brushes some toner over the photoconductor. Since opposite charges attract, the latent image attracts toner particles and becomes coated with black or whatever color toner you're using. The latent image becomes a visible image. Here's an example. Remember the charge process? We demonstrated one way that things develop a static charge, by being rubbed against something. Our demonstration earlier used this process to create a charge on a piece of acrylic plastic. There's a special name for a charge that builds up from mechanical action. It's called a triboelectric charge. You'll see in a minute what it has to do with development. Okay, imagine this cylinder is the photoconductor drum. It's sitting like this inside a copier. Somebody wanted to copy and push the print button. The drum began turning. It was charged here. Still turning, it was exposed here. Still turning, and now after exposure, there's a latent image on the surface ready to be developed, moving down to about here. The charge on a real photoconductor is electrostatic, while the charge on the developer is triboelectric. For this demonstration, I can simulate the developing action by putting some triboelectric charge on our imaginary drum. Okay, here it is, a charged photoconductor, ready for development. By letting it attract an appropriate material, the latent image can be made to appear just like this. The drum turns, the latent image comes in contact with the development system, and what was invisible can now be seen. You see how the surface has randomly picked up these bits of paper? This is because by rubbing it, I created an even triboelectric charge on the surface. There's no detail, nothing you'd really call an image. But If I had a way to charge this surface selectively, as a copier does with its exposure system, then after development, you would have seen something like this.
As the photoconductor drum rotates, the latent image approaches the development roller. The roller's surface is coated with developer, a mix of toner and carrier. The toner carries a charge opposite that of the latent image. For our example, the latent image is positive, so the toner is negative, shown in green. Toner and carrier both start out in a neutral condition, but as they rub together inside the development unit, a triboelectric charge builds up between them. This causes toner to stick to the carrier. The development roller is magnetic, so it attracts the iron-based carrier beads, each one with a coating of toner. This forms an even layer of developer on the roller called a magnetic brush. As the roller turns, it brushes developer over the surface of the drum. Since toner has an opposite charge, it's attracted to the latent image. The toner particles are pulled away from the carrier beads onto the photoconductor. In this way, the entire latent image becomes coated with toner. Electrical attraction will hold the toner in place until it's transferred to a sheet of paper. The development system has to maintain the proper ratio of toner to carrier with a high degree of accuracy. If a copier is running with too much toner in the system, it can contaminate the inside of the machine like fine dust. To maintain copy quality and keep the machine running clean, most copiers have a system that monitors the concentration of toner in the development roller's magnetic brush and adds toner to the development unit only when the concentration falls too low. This type of system exposes and develops a small test patch on the photoconductor once about every 10 copies. A photosensor checks the density of toner on the test patch by reading how much light it reflects. The brightest reflection would be from the bare drum surface and the darkest from a very thick coating of toner. If the patch isn't dark enough, that means there's not enough toner in the development unit to provide a suitable concentration in the magnetic brush. To correct this undertoned condition, the copier's control system triggers a toner supply mechanism. It's often a special roller inside the development unit that scoops up a small amount of toner with grooves or ridges and then drops it into the development unit. As soon as image density is dark enough, this mechanism is shut off to prevent too much toner from entering the system. This method keeps the ratio of toner to carrier balanced for an average copy, but isn't responsive enough to change image density one copy at a time. It also can't cope with the presence of toner background that can appear even with a clean original. For this level of control, the machine needs a system that responds with an immediate change in image density. Some machines adjust image density for individual copies by varying the brightness of the exposure lamp, as mentioned in the last section. Image density can also be controlled by a special electrical system that works in conjunction with the development unit. It's called the bias circuit, and it works like this. During development, toner is attracted to the latent image because they have opposite charges, usually negative toner and positive latent image. Imagine what would happen if the development roller had a stronger positive charge than the latent image. The toner would have a stronger attraction to the roller than to the drum and wouldn't leave the magnetic brush. That's how the bias circuit works. In response to information from manual or automatic image density controls, the copier's main board sends a bias control signal to a high-voltage power pack. The power pack then produces a bias voltage that corresponds directly to the control signal. This voltage is applied to the outside of the development roller during the entire copy cycle. It creates enough electrical attraction on the roller to hold back a certain amount of toner during development. To produce a lighter copy, the main board increases the bias voltage to hold back even more toner. This reduces the amount that's attracted to the latent image, resulting in a relatively thin deposit of toner on the drum. For a darker copy, the main board lowers the bias voltage, so very little toner is held back on the development roller. The result, a greater thickness of toner on the latent image and a darker copy. Inside the toner supply, there's often an agitator to keep the particles from clumping together. Here's an agitator in the development unit. It mixes newly added toner with the existing supply of carrier to create and distribute the triboelectric charge. This is a paddle roller. It feeds the toner and carrier mixture to the development roller. Almost touching the development roller is the doctor blade. It determines the height of the magnetic brush by scraping off excess developer as the roller turns. In a desktop copier, the moving parts in the development system are driven from the main motor by a system of belts, gears, or both. Typically, motor drive is transmitted to one gear on the back of the development unit. This gear engages others on the unit and transmits appropriate rates of rotation to all the moving parts in the system.
With development, we passed a new milestone in the process, a visible copy of the original. The key elements are the toner and carrier. They're mixed together in the development unit to make a charged ferromagnetic developer, which is picked up by a magnetic roller and brushed onto the photoconductor. The toner is attracted to the latent image because of its opposite charge. Electronic and mechanical subsystems control toner supply, developer mixing, and image density. All that brings us to right about here. We have an image, but before it can become usable copy, we have to get a sheet of paper into the picture. And that's what happens in the next step in the process, paper feed. When people say, "I'll send you a copy," what they usually mean is they'll send you some written information on a piece of this stuff, paper. For centuries, paper has been the vehicle for carrying information from one place to another. And in spite of all the electronic sophistication in today's office automation systems, there's still nothing quite as convenient as something you can fold up and put in your pocket. In the last section, we saw how the latent image becomes a visible toner image through the action of the development process here. The toner is now in place on the drum, ready to be moved to a sheet of paper. But first, we have to feed the paper into the copier. For copier applications, a paper feed system has to take care of three separate functions: transport, separation, and registration.
Transport is the most obvious of the three. Paper has to move through the copier at the right speed and with the right timing. Paper separation is a requirement for any sheet-fed copier. Since the machine takes paper from a stack of possibly thousands of sheets, it needs a way to make sure only one sheet is fed for each copy cycle. Paper registration is a matter of making sure the sheet is properly lined up with the latent image. The exposure system guarantees that the image is straight on the drum. A registration mechanism guarantees that each sheet of paper is straight when it meets the latent image, so a finished copy shows the same alignment as the original.
Copiers manage paper transport with components that are simple and reliable: rubber belts or rollers. Rubber is an unusual material. It grabs onto other surfaces so well because of friction and flexibility. A sheet of paper is not perfectly smooth. It's pressed out of lots of fibers. And as you can see in this close-up photo, it has many irregularities on the surface. If you try to grab this surface with something hard, like metal, you'd run into a few problems, because most of the surface is actually recessed below the top fibers. To move paper effectively, you need something that can mold itself to the irregular surface and create a more secure grip, like rubber. Even this small rubber eraser grabs the paper very securely and moves it wherever it needs to go. There's another advantage to rubber. With a little pressure, it flattens slightly,
and the area of contact between the roller and paper increases even further. Okay, now that you know how rollers move paper around, let's look at how they're used for more specific jobs, like separation. Remember, paper separation is the process of pulling a single sheet from the supply to avoid a multiple feed.
One separation method uses a cork pad mounted under the first feed roller. The pad is positioned so that a sheet of paper from the supply must pass over it before entering the copier. When the feed roller starts pulling the top sheet into the machine, sometimes the sheet underneath sticks to it. This can happen simply from the friction between the two sheets. The friction between the bottom sheet of paper and the cork pad is greater than the friction between the two sheets of paper, so the pad holds the bottom sheet back. Only the top sheet feeds into the copier. The bottom one will feed on the next copy cycle. Another separation mechanism uses a pair of rollers. The top roller is coupled directly to the drive system and is always driven forward. The bottom roller is driven in reverse, but through a clutch mechanism that lets it turn forward if enough force is applied. Here's how it prevents multiple feeds. If the feed roller picks up a single sheet from the supply, forward rotation is transmitted through the paper to the bottom roller. The clutch releases and the bottom roller turns forward as well. But if two sheets are picked up, the friction between them isn't strong enough to force the bottom roller to rotate forward. It reverses. This action separates the top sheet of paper and prevents the bottom one from feeding.
Okay, we've covered the basics of transport and separation. The next step is paper registration to prevent skewed images on copies like this. Most copiers use a pair of registration rollers mounted just past the feed rollers. The machine's timing is set so the registration rollers stop just before a sheet of paper hits them, even though the feed rollers are still turning, pushing the sheet forward.
This forces the sheet to buckle slightly on contact and align its leading edge with the rollers. The sheet is now square in the paper path, ready to receive an image. In most copiers, the drive for paper feed components comes from the main motor and is transmitted to each roller by a system of belts and gears. Since feed rollers have to supply paper according to the precise timing of a copy cycle, they're usually driven through some kind of clutch.
A clutch is a type of mechanical link between two different assemblies that can make them engage or disengage as required. Most of us are familiar with the clutch in a car. It provides the link between the engine and transmission. In a paper feed system, clutches link drive gears to rollers. Motor drive can be passed to a roller or taken away so the rollers start or stop turning as necessary. The pieces making up a clutch are designed so that one side can be turning while the other side is stationary. When it's time to engage a roller, an external mechanism causes both sides of the clutch to lock together and transmit motor drive as if it were a solid piece. This is a spring clutch. It's basically a tightly coiled spring surrounded by this sleeve. Inside the spring are two drive pieces. One supplies rotation from the copier's motor, while the other transmits that drive to a roller. Under normal circumstances, the spring grips both pieces very tightly, so both sides of the clutch turn as one unit. To release the clutch, an actuator forces one side of the spring to expand. It moves away from the drive piece inside, so motor drive is removed and the roller stops turning. A spring clutch needs some type of electronic control, and that's usually a solenoid, a type of electromagnetic actuator. A solenoid is very simple. It's a hollow electromagnet with a metal plunger partially inserted inside. When power is applied to the magnet, it creates a strong magnetic field. This field grabs hold of the metal plunger and pulls it all the way inside. If something is attached to the plunger, it gets pulled too. There's another type of clutch that's sort of a clutch and solenoid in one unit, a magnetic clutch. It uses two plates, one driven and one idle, something like the clutch in a car. To activate a roller,
The copier energizes the electromagnet, which pulls the two plates together. Now turning like a solid piece, the clutch transmits drive through the center shaft and onto whatever component needs turning.
By activating and releasing magnetic clutches and solenoids, the copier's control system can start and stop the paper feed rollers very precisely. This sort of accurate control is possible not only because of clutches and solenoids, but also because of sensors in the paper path. Paper path sensors are often hybrids with mechanical and photoelectric components. Many use a small actuator lever, which every passing sheet pushes down, raising the lower portion out of a photointerrupter. They're positioned to let the control system know when a sheet of paper has reached certain key locations, so that other systems can be activated according to the proper timing. If a sensor detects that a sheet has remained in one spot for too long, the control system knows there's a problem and indicates a misfeed. Other sensors tell the control system what size paper is being used. Sometimes they detect the position of adjustable fences in the paper supply. As the fences are adjusted for a certain width and length of paper, a corresponding sensor is triggered. In copiers that use removable paper cassettes, a group of switches detects the configuration of special tabs or notches on the cassette. Each paper cassette will activate only certain switches in the group. The resulting combination of open and closed switches corresponds to a specific paper size. The electronics controlling a paper feed system are technically simple, but can become complex simply from the number of elements involved. A basic desktop copier has at least 3 sensors in the paper path: paper end, registration, and exit. The same machine might have 2 solenoids controlling paper transport on the feed and registration rollers. Electronically, the arrangement of these components is very straightforward. Sensors bring information to the main board, and the appropriate control devices carry out the instructions. The paper feed system for a large copier with a high-speed document feeder and sorter is much more complex. It might have dozens of sensors and solenoids, each sensor independently monitored, each solenoid individually controlled.
This complexity facilitates high performance and also helps the operator troubleshoot problems in the paper path. While the technology of the paper feed system is by no means unique to electrostatic copiers, it's still a vital part of the copy process. Paper feed systems rely on rubber belts and rollers to grab sheets of paper one at a time and feed them through the copier. Other rollers, or friction pads, handle paper separation and registration. Sensors in the paper path enable the control system to maintain the correct timing during a copy cycle, monitor paper size, and detect misfeeds. At this point in the copy cycle, a toner image has been created on the photoconductor, and a sheet of paper is on its way through the feed system. The next process brings the paper and toner together. It happens right here. We'll cover it in the next section on transfer and separation. Up to now in the copy process, all we have is a blank sheet of paper moving into the machine and an image of the original in the form of a thin layer of toner on the photoconductor. But the paper and the image are in 2 different places. 2 almost simultaneous processes take place next. The toner image is transferred to the paper, and the paper is separated from the photoconductor so it can move through the rest of the machine. At this point, the paper is about here, moving toward the drum, and the developed image is on the photoconductor, approaching the transfer and separation corona units here. These coronas are very similar to the charge corona, metal housings, each with a thin wire running down the center. Like the charge process, transfer and separation rely on the action of electrical fields produced by these corona units. One field pulls the toner onto the paper, and a second field pulls the paper away from the drum.
The electrical attraction created during transfer is similar to the effect of competing magnetic fields, the kind of thing you see in the motion of a compass needle. A compass works because of a weak magnetic attraction. A small magnet in here reacts to a very big magnet, the Earth, and is always attracted to magnetic north. But if I bring another magnet into this picture, things begin to change. The Earth's magnetic field may be large, but it's not very strong. Over short distances, this one is much stronger. When it's brought near the compass, there's no contest. The stronger magnet wins, and the needle is pulled away from magnetic north. Here's how this type of relationship applies to the transfer process. Imagine this as a cross-section of a photoconductor drum, and this thin magnetic strip on the edge is the latent image. Since we're at a point after development, the latent image is coated with a layer of toner held in place by electrical attraction. These ball bearings represent the toner. After development, the drum keeps turning, and the toner on the latent image is brought near the transfer corona. You can see what's going to happen in this model. It's another case of a strong attraction encountering a weaker one. In a copier, the transfer corona creates an electrical charge stronger than the latent image. The result, when the drum turns past the transfer corona, the toner is attracted away from the photoconductor. There's one other element: paper. The paper feed system is timed so that just as the developed image reaches the transfer area, a sheet of paper is being pushed up against the drum. It happens like this.
After development, the drum's rotation brings the image toward the transfer area. The image now has two components: the latent image, defined only by electrical charge, and the visible toner image, held in place on the photoconductor by electrical attraction. In response to a high DC voltage, the transfer corona generates a positive electrical field around the corona wire. The field spreads out, carrying a positive charge toward the drum. A sheet of paper enters the transfer area. In a real copier, the paper moves at exactly the same speed as the drum and is pushed into direct contact with the surface. The gap shown here is only for illustration. Once the paper is over the transfer corona, it receives the positive charge, a stronger charge than the one holding the toner to the photoconductor. The stronger charge wins. Toner is attracted away from the latent image onto the paper. The charge on the paper holds the sheet flat against the photoconductor to prevent the image from smearing. After transfer, paper and photoconductor move over the separation corona. This corona wire is supplied with an AC voltage. It produces an oscillating electrical field which breaks the attraction between photoconductor and paper. With the force of attraction neutralized, the paper's own stiffness usually separates it from the photoconductor, though curled or unusually thin paper may continue to stick. Pick-off pawls provide a mechanical backup for electrical separation. These small, sharp fingers ride against the photoconductor and strip off any paper not separated by the corona. We finally have something that looks like a copy, though not yet a permanent one. But after transfer and separation, there's enough electrical attraction present to hold the toner in place until it's bonded to the paper. For successful transfer to take place, the electrical charges on the drum, toner, and paper must be suitably balanced. If there's too much charge on the drum, the attraction between latent image and toner is too strong for the corona to overcome, and the toner won't transfer completely. Rather than reducing drum charge, some copiers avoid this problem by using a pre-transfer lamp, positioned close to the photoconductor between the transfer corona and the development unit. Light from the pre-transfer lamp reduces the latent image charge and therefore weakens its attraction. Not enough to cause the toner to drop off, but enough to assure an effective transfer. Reducing the drum charge also prevents toner particles from being attracted back to the drum during separation. The circuits driving the transfer and separation coronas are virtually identical to that used for the charge process. And in some copiers, the transfer and charge coronas share the same power pack. The separation corona differs in that it gets an AC voltage. So in some machines, a separate power pack is required.
The copy cycle is almost finished. At this point, the original image and a sheet of paper have finally been brought together. Using an electrical attraction stronger than the latent image, the transfer corona pulls the toner from the photoconductor to the paper. The separation corona then neutralizes some of the charge on the paper, enabling the paper's own stiffness to pull it away from the drum. If separation isn't complete, pick-off pawls provide a mechanical means to strip the sheet from the drum surface and guide it back into the paper pad. Now we have this. A copy. A visible image of the original on a sheet of paper, but it's not quite ready to send out with the annual report. The image is supported by paper, but not attached to it. To make the copy permanent, this toner-paper combination has to go through one more process. We'll cover it in the next section, fusing. If you want to see how something can be permanently bonded to a surface, this is the kind of hardware to examine. It uses exactly the right technology for the job. In this section of the program, we're going to look at some very similar technology that's used inside a copier. In the last process, toner was transferred from the latent image to a sheet of paper, and then the paper and toner together were separated from the photoconductor drum. That happened right here in the transfer area. At this point, the original image is on the paper, but it's held in place only by a relatively weak electrical charge. To turn this into a usable, permanent copy, the toner must be fixed in place on the paper. That happens right here in the fusing system. After separation, the paper moves away from the drum over to this point, where it passes between two rollers. The rollers press together, and the top one is heated. Remember, toner is made from a type of resin. It melts at about 180 degrees Celsius. So with this combination of heat and pressure, the toner is both melted and pushed into the paper. The combination makes an excellent bond. It happens like this. For the purpose of our demonstration, here's a sheet of paper with a toner image on it, still just sitting there. See? To turn this into a permanent copy, we apply heat and pressure at the same time. This is a dry mount press. It's the kind of thing used in the graphics industry to mount photographs and certain types of artwork on a flat surface. Right now, some special material on the back of those letters is being melted and pressed into the paper. When the heat is removed, it will cool very quickly and make an excellent glue to hold the letters on the surface. And here we are, a finished copy. This is exactly what happens inside a copier. The fusing system creates a faster version of the demonstration we've just seen. Toner is bonded to the paper through a carefully controlled application of pressure and heat.
During a copier's warm-up period, the fusing temperature is raised to a level hot enough to melt toner. A control circuit maintains this temperature for as long as the machine is turned on. When a copy cycle begins, the rollers start turning. Here comes a copy fresh from transfer and separation. It carries a developed image, but the toner is only held in place on the paper by electrical attraction. The fusing rollers press together with considerable force and rotate in opposite directions to draw the paper through. When the sheet passes between the rollers, the toner is melted and at the same time pushed deeper into the paper fibers. This happens over the entire sheet. The image that was exposed, developed, and transferred is now fused to the paper, a permanent copy. While the earlier processes captured the original's appearance, fusing matches or improves the original's durability. To function properly, the fusing system has to maintain three things: heat, pressure, and lubrication. Heat comes from an incandescent lamp mounted inside one of the fusing rollers. At initial power-up, the lamp is switched on and a thermistor monitors the rising temperature. As the heat approaches the fusing level, the lamp is pulsed on and off to keep the heat from rising too rapidly. When fusing temperature is reached, the control system maintains it at the correct level by switching the lamp off and on in response to the heating and cooling in the system. Because it produces so much heat, the fusing system in any copier always has some kind of overheat protection. In some machines, it's a relay that cuts off power to the fusing lamp when a critical temperature is reached. Another form of protection is provided by a thermal fuse mounted near the heated roller. If the temperature rises too high, the fuse opens, cutting off power to the lamp. The fusing rollers must allow for the small amount of separation that occurs when a sheet of paper passes between them. One roller is always flexibly mounted to give a little with each copy. Small adjustable springs provide the pressure and enable the force of the two rollers to be changed for different thicknesses of paper. Roller composition also has an effect on pressure. The hot roller is usually Teflon. It withstands high temperatures and has a smooth, slippery surface. The other roller is silicone rubber. Since the Teflon roller has a hard surface, the other one must be made from a flexible material to get a grip on the paper. The silicone variety also withstands heat without breaking down. The use of Teflon for the hot roller helps prevent copies from sticking to it, but this material by itself can't avoid the problem completely. Most copiers have a fusing lubrication system that coats the rollers with a layer of silicone oil. This keeps toner from sticking to the roller surfaces to prevent fuser jams and the appearance of toner after images on subsequent copies. Silicone oil is stored in a small reservoir and pumped into the fusing system during each copy cycle. The oil soaks into an absorbent pad that applies it to the hot roller, while a long blade spreads the oil into an even coating as the roller turns. Rotation for the fusing rollers comes from the copier's main motor, transmitted through a series of gears. The rollers turn constantly for the entire copy cycle, so electronically controlled clutches are not needed. The fusing rollers push the copy through to an exit roller, which feeds it into a tray on the outside of the machine. This is the first time a user sees the results of the copy process. A typical fusing control circuit involves low-voltage electronics on the main control board and high-voltage components isolated on a separate board, often the same one that drives the exposure lamp. Temperature indications from the fusing thermistor go to the main board, which responds by sending the appropriate control signal to the high-voltage board. The signal will ultimately find its way to a triac, or other high-voltage device, which controls power being sent to the lamp. If a thermal fuse provides the overheat protection, it will always be mounted in series with the lamp. If the fuse opens, the lamp goes out.
In the fusing process, a sheet of paper carrying a toner image passes between two rollers. Heat from an incandescent lamp melts the toner, and at the same time, pressure from the roller forces the toner into the paper fibers. The result is a bond more durable than ink on most original documents. Up to now, we've seen what it takes to make a copy, from charge through fusing. And though fusing is the last step needed to make one copy, it isn't the final process in a machine designed to make lots of copies. For a copier to be able to make many copies on the same photoconductor, there's one more process required: cleaning. In the previous sections of this program, we examined the 6 major processes by which an electrostatic copy is made. First comes the charge process, then exposure, followed by development and paper feed, transfer and separation, and finally, fusing. Now, a copy's been created and a person's needs satisfied, but what about the next person? All the processes we've seen so far are aimed at producing a single copy. But to be practical, the machine has to produce many copies from different originals. The photoconductor is engineered with this in mind. It has a continuous surface, so it can return to the starting point in a copy cycle and begin the sequence again. That starting point is right here, just before the charge corona. By the time a portion of the surface gets here, it has to be ready for use again, so the whole process can be repeated. But there's a problem. The photoconductor isn't clean. Think of it like this white board. This surface has just done the job of carrying information, an illustration of the copy process. Before it can be used for something else, it has to be cleaned. And the same thing goes for the photoconductor. The copier has to remove 2 things from the photoconductor before it can make another copy. The first is leftover toner. Though most of the toner applied during development is transferred to a sheet of paper, a small amount is left behind on the drum. The second thing to remove is residual charge. After transfer, most of the toner is gone, but the latent image is still there. If the photoconductor were used for another copy without removing leftover charges and toner, then an image of the last copy would appear on the new one. There are 2 separate systems to prevent this from happening. This is the cleaning unit. It uses mechanical action to remove leftover toner. Just past it is the quenching lamp, which shines light on the photoconductor to remove the latent image. Together, these systems restore the surface to the physical and electrical condition it was in before the charge process. Just as an eraser removes the image from this white board, the cleaning and quenching processes remove all trace of an image from the photoconductor. The surface is returned to a neutral state, ready for another copy cycle.
As the drum turns, the latent image on the photoconductor moves from the separation area to the cleaning system. The latent image first encounters a cleaning brush, which loosens toner particles still held in place by electrical attraction. Right after the brush is a cleaning blade that scrapes the surface clean of any remaining toner. Mounted just past the cleaning blade is the quenching lamp. It shines light onto the photoconductor during the entire copy cycle. As in the exposure process, light switches the surface to its conductive state. The latent image and any background charge are completely removed. The photoconductor is now in a physically clean and electrically neutral condition, ready to repeat the copy process. Because of the cleaning system's physical contact with the photoconductor, the individual components must be designed to avoid damaging the surface. The bristles on the cleaning brush are made from polyester or carbon fiber. They're completely non-abrasive and slide easily over the surface. The cleaning blade is a flexible plastic. It's attached to the cleaning unit only at one point, at the exact center of the blade. It always stays parallel with the drum and applies even pressure, minimizing wear on the surface. Many copiers go a step further and push the cleaning blade up to the drum only during the copy cycle. Just before the main motor starts turning, a solenoid pulls a lever on the cleaning unit that presses the blade up to the drum. When the motor stops, the solenoid releases and the blade retracts. Small copiers generally collect used toner in the cleaning unit itself. After it falls from the cleaning brush, the toner is moved into a storage tank by some type of transport mechanism. This particular unit pushes toner into the storage tank from the bottom, so an actuator at the top begins to rise as the tank fills up. When the tank is full, the actuator rises high enough to break the light path in a photointerrupter. The control system detects the change and alerts the operator that the used toner tank needs replacing. Some copiers have a used toner recycling system. In this type of cleaning system, toner collected from the drum is moved back to the development unit with a mechanical transport device, something like this rotating auger. While this system offers the advantage of recycling, it also tends to deposit unwanted paper fibers and dust in the development unit along with the toner. Over a long period, this type of developer contamination can lead to reduced copy quality, so most of today's machines simply collect used toner for disposal. The quenching lamp is similar to the pre-transfer lamp sometimes used before transfer and separation. Some copiers use a neon tube or fluorescent lamp for quenching, while others use a row of LEDs or small incandescent lamps. In each case, the effect is the same, an even, unfocused light directed over the full width of the photoconductor. Rather than using a quenching lamp alone, some copiers use another corona to help remove residual drum charge. This quenching corona can be mounted just before the lamp, or the lamp and corona can be combined into a single assembly, as seen here. A quenching corona produces a high-voltage electrical field that applies a positive charge to the drum surface. This field neutralizes any negative charge that may exist on the drum. Then the quenching lamp removes all remaining photoconductor charge. Combining the effects of charge and light, this two-step method is used primarily with the cleaning systems in larger, high-speed copiers.
Cleaning is the final process in the copy cycle. It turns the complex technology of a copier into a source of low-cost reproduction by making the photoconductor reusable. After transfer and separation, the copy continues on to the fusing system, while the photoconductor moves into contact with the cleaning unit. This removes all traces of the last copy. Leftover toner is taken off the photoconductor with a cleaning brush and blade. The toner is either collected for disposal or recycled in the development unit. After physical cleaning, the latent image itself is removed, neutralized by light from a quenching lamp, or by an opposite charge from a quenching corona. That's the end of the copy process. A copy has been produced and the photoconductor prepared for making more. Through the course of this program, we've seen some of the history of office automation and the evolution that's occurred in the way people make copies. From carbon paper right up to modern electrostatic reproduction.
We've examined the copy process in some depth, looking at the individual steps involved, their requisite technology, and the reasons behind them. It's also important to understand the role copiers have come to play in the world of office automation. In today's business environment, it's essential to disseminate information strategically. You have to get the right information to the right people and in the right form. This is why copier technology is so vital. No matter how sophisticated your communications and data processing systems are, sooner or later, somebody's going to want to see something on paper. Doing business is still a matter of managing information, and the better you manage it, the more successful your business will be. The appearance of the business office may have changed over the years, but the need for effective information management will always be with us.
Today, that need is the force that drives the evolution of office automation. When this office was new, it was the catalyst for the invention of the copy process.